This video is for educational and entertainment purposes only. Automotive repair and diagnostics involve inherent risks, including the potential for serious injury, property damage, or death. The information provided in this masterclass is based on historical trends and case studies and does not constitute professional mechanical advice. Every vehicle is different, and manufacturer-specific procedures must always be followed. Before attempting any inspection or repair, you must consult your vehicle's service manual and follow all safety protocols, including the use of jack stands, eye protection, and proper ventilation. If you are unsure of your ability to perform a task safely, consult a certified professional mechanic. By continuing to watch this video, you acknowledge that you are proceeding at your own risk and are responsible for your own due diligence. The most expensive light in the world is not a designer chandelier or a high-end architectural fixture. It is a small amber icon on your dashboard that looks like a simplified engine. Statistics suggest that the average American driver will spend over $65,000 on vehicle maintenance and repairs over their lifetime. However, historical data indicates that nearly 30% of that expenditure is often directed toward unnecessary parts, labor for misdiagnosed issues, or preventative maintenance that was performed far too late. Imagine walking into a doctor's office, and instead of describing your symptoms, you simply point to your chest and hand over your credit card. That is exactly what most drivers do when their car begins to fail. They allow the machine to speak a language they do not understand, and they pay a premium for a translator. Today that changes. This is the first part of a 10-part deep dive masterclass designed to turn you from a passive passenger into a diagnostic expert. We are going to deconstruct the wall between the driver's seat and the engine bay, teaching you to interpret the complex data streams, sensory signals, and mechanical rhythms that your car uses to communicate its health. By the end of this series, you will understand how to identify a failing oxygen sensor before it destroys your catalytic converter, how to distinguish between a minor vacuum leak and a catastrophic internal failure, and how to navigate the high-stakes world of automotive repair with the confidence of a professional. To understand where we are going, we have to understand the sheer complexity of the modern vehicle. Your car is no longer just a collection of gears, pistons, and belts. It is a high-performance mobile supercomputer. In the 1960s and 70s, diagnosing a car was almost entirely a sensory experience. You adjusted the carburetor by ear, you checked the timing with a strobe light, and you felt for the mechanical flat spot in acceleration. Today, a typical mid-range sedan contains between 30 and 100 separate electronic control units, or ECUs. These computers are networked together, constantly whispering to each other across a digital highway known as the Controller Area Network, or CAN bus. When you press the accelerator, you aren't just pulling a cable. You are sending a request to a computer which then analyzes the engine temperature, the intake air density, the gear ratio, and the traction levels before deciding exactly how much fuel to spray into the cylinders. Because of this complexity, the check engine light is not a simple on-off switch. It is the end result of millions of calculations. The history of this communication system began in earnest with the 1996 federal mandate in the United States that required all vehicles sold to be equipped with OBD2, or Onboard Diagnostics version 2. Before this, every manufacturer had their own proprietary language. A Ford technician couldn't talk to a Toyota, and a backyard mechanic was essentially blind. The implementation of OBD2 was a revolutionary moment for consumer rights because it standardized the port through which the car speaks. This 16-pin connector, usually hidden under your dashboard, is the gateway to the car's soul. However, many people make the mistake of thinking that a code tells you exactly what part to replace. This is the most common and expensive misconception in the automotive world. If your car throws a code for a lean condition, it does not mean the oxygen sensor is bad. It means the sensor is doing its job and reporting that there is too much air and not enough fuel in the system. The actual cause could be a cracked rubber hose, a clogged fuel filter, or a failing fuel pump. Replacing the sensor is like shooting the messenger for bringing bad news. In this masterclass, we are going to learn how to look past the messenger and find the source of the problem. Let's look at a case study involving the P0300 code, which is one of the most common and frustrating codes a driver can encounter. This code signifies a random or multiple cylinder misfire. To the untrained eye, this looks like a sign to replace all the spark plugs and ignition coils immediately. A driver might spend $400 on parts only to find the light remains on. Through a systematic diagnostic approach, we see a different story. By looking at the freeze frame data, which is a snapshot of what the car was doing the exact moment the fault occurred, we might see that the misfire only happens when the engine is at high load and low RPM. This points away from the spark plugs and toward a potential fuel delivery issue, or an exhaust gas recirculation valve that is sticking open. Understanding these nuances is the difference between a $10 fix and a $1,000 mistake. Beyond the digital codes, we must also master the 5 senses diagnostic method. Your car will often tell you it is failing long before the computer realizes it. For example, consider the sense of smell. If you step out of your car after a long drive and smell something sweet, like maple syrup, you are likely smelling ethylene glycol, the primary ingredient in engine coolant. This is a critical warning sign. If you ignore that smell, the potential outcome is a warped cylinder head or a blown head gasket, which can cost more than the value of an older vehicle. Conversely, if you smell rotten eggs, your car is telling you that the catalytic converter is overheating because the engine is sending unburned fuel into the exhaust. This isn't just an emissions problem. It's a sign that your engine is running rich, which could be caused by something as simple as a dirty mass airflow sensor. We also have to discuss the auditory language of the vehicle. A chirp that increases with engine speed is almost always a sign of a glazed serpentine belt or a failing pulley bearing. A knock that happens when you go over bumps is usually a sign of worn-out sway bar links or strut mounts. But a deep metallic thud from the engine block is the sound of a connecting rod bearing that has lost its lubrication. Learning to distinguish between these sounds is essential. In this series, we will break down the frequencies and rhythms of these noises, so you can identify them with surgical precision. The financial stakes of this knowledge cannot be overstated. In the United States, labor rates at dealerships can range from $150 to over $250 per hour. Often you are charged for diagnostic time, which is the hour the technician spends plugging in a scanner and performing the very steps we are going to cover here. By performing your own preliminary diagnostics, you shift the power dynamic. When you walk into a repair shop and say, "I have a P0442 code and I've already inspected the gas cap seal and the evaporative purge valve," the technician knows they are dealing with an informed consumer. This drastically reduces the likelihood of being sold unnecessary system flushes or redundant repairs. Throughout this masterclass, we will also dive into the Mode 6 data. This is the raw, unedited data that the car's computers use to run self-tests. Long before a check engine light turns on, the car is performing monitors. It is checking the efficiency of the catalyst, the integrity of the fuel system, and the performance of the oxygen sensors. If a component is degrading but hasn't yet reached the failure threshold, it won't trigger a light, but the data is there in Mode 6. We will show you how to read these hexadecimal values to predict a failure weeks or even months before it happens. This is the level of predictive maintenance that fleet operators use to keep millions of miles on their vehicles, and now you will have access to that same methodology. We will also address the parts cannon phenomenon. This is a term used by professional mechanics to describe the act of throwing new parts at a car in the hope that one of them fixes the problem. It is the most inefficient way to repair a vehicle. We will teach you the verification step. Every time you think you found a failed component, we will show you how to test it before you buy a replacement. For example, if you suspect a fuel pump is failing, we don't just swap it out. We perform a fuel pressure test and a fuel volume test. We check the relay for voltage drop. We ensure the ground wire has a solid connection. Only when the data confirms the failure do we spend the money. This methodical approach is the core of the diagnostic mindset. As we move forward in this series, we will get into the specifics of various systems: the charging system, the cooling system, the drivetrain, and the braking system. But it all starts here with the realization that your car is a logical machine. It does not act crazy or unpredictable. It follows the laws of physics and the logic of its programming. When a car fails, it is simply reacting to an input that is outside of its expected parameters. Your job is to find that input. Whether you are a student looking to maintain your first car, a commuter trying to lower your cost of ownership, or an enthusiast wanting to understand the why behind the how, this masterclass is your roadmap. We are going to take the mystery out of the machine and put the control back into your hands. This is not just about saving money. It is about the security of knowing that you can trust the machine that carries you and your family every day. Prepare yourself, because we are about to go much deeper than just reading a code. We are going to learn how to think like the computer that runs your car. To understand the brain of your vehicle, we have to look at the Engine Control Module, or ECM, as a master conductor of an incredibly fast-paced orchestra. In 2026, The speed at which these processors operate has reached levels that were reserved for high-end gaming rigs just a decade ago. Imagine Alex, a commuter in a busy U.S. metropolitan area, driving a 2023 crossover that has just reached 3 years of age. Alex is cruising at 65 miles per hour on the interstate when a slight hesitation occurs. To Alex, it felt like a tiny hiccup. To the ECM, it was a data event involving over 5,000 individual calculations that happened in the span of a single millisecond. The ECM operates on a constant feedback loop of inputs and outputs. To master diagnostics, you must first categorize every component into one of these two camps. Inputs are the sensors, the eyes, ears, and nose of the car. Outputs are the actuators, the muscles that actually do the work. If the car is running poorly, the problem is either that the brain is receiving bad information from a sensor, or it is giving a correct command to an actuator that is physically unable to respond. Let's look at the most critical input in the entire system: the mass airflow sensor, or MAF. Historical trends show that the MAF is one of the most misunderstood components in the engine bay. Its job is to measure the literal weight of the air entering the engine. Because air density changes based on altitude and temperature, the computer cannot just measure the volume of air. It needs the mass. The MAF uses a tiny, heated wire through which it passes an electrical current. As air flows over that wire, it cools it down. The computer has to apply more current to keep that wire at a constant temperature. By measuring how much current is required to keep that wire hot, the ECM calculates exactly how many grams of air per second are entering the intake. Imagine if a tiny speck of dust or a film of oil from a poorly maintained air filter coats that wire. The wire is now insulated. It doesn't cool down as fast as it should. The ECM thinks less air is entering the engine than actually is. Consequently, it commands the fuel injectors, the actuators, to spray less fuel. The result is a lean condition, where the engine has too much air and not enough gas. Alex experiences this as a stumble during acceleration, but because the sensor is still sending a signal that is technically within a legal voltage range, the check engine light might not even turn on yet. This is what we call a pending code or a soft fault. This brings us to the concept of fuel trims, the single most important data point for any diagnostic masterclass. If you learn nothing else today, learn how to read short-term and long-term fuel trims. Think of fuel trim as the computer's honesty report. The ECM has a pre-programmed map of how much fuel it thinks the engine needs at any given RPM and load. This is called the base map. However, because parts wear down and weather changes, the ECM uses the oxygen sensors in the exhaust to see if it actually got the mixture right. Short-term fuel trim, or STFT, is the immediate reaction. If the oxygen sensor reports too much oxygen in the exhaust, the STFT will jump to a positive number, perhaps plus 10%. This means the computer is adding 10% more fuel than the base map originally called for to correct the lean condition. Long-term fuel trim, or LTFT, is the history of these corrections. If the STFT stays high for too long, the computer moves that correction into the long-term memory. In our case study with Alex, if we saw an LTFT of plus 25%, we would know immediately that the computer is desperately trying to compensate for a massive air leak or a fuel delivery shortage. In the US, the threshold for triggering a check engine light is typically 20 to 25%. If Alex's car is at plus 18%, it is running terribly, but the dashboard remains dark. This is why professional diagnostics start with a scanner, even when no light is present. We are looking for the struggle happening behind the scenes. Now let's talk about the logic gates the ECM uses to decide when to trust its sensors. This is known as open loop versus closed loop operation. When Alex first starts the car on a cold morning in 2026, the oxygen sensors are cold. Oxygen sensors do not work until they reach approximately 600 degrees Fahrenheit. During this warm-up period, the car is in open loop. It ignores the oxygen sensors and runs entirely off the pre-programmed base map and the engine coolant temperature sensor. If your car runs perfectly when you first start it, but starts acting up after 5 minutes, your problem is almost certainly a sensor that only comes into play during closed loop, such as a skewed oxygen sensor or a failing catalytic converter. Step by step, a diagnostic path should follow the path of least resistance. Let's take a common scenario: AP0302 code, which indicates a misfire on cylinder number 2. A novice would immediately buy a new spark plug. A masterclass student would swap the ignition coil from cylinder 2 to cylinder 3, and the spark plug from cylinder 2 to cylinder 1. This is a zero-cost diagnostic move. If the code moves to P0303, you know the coil was the problem. If it moves to P0301, it was the plug. If the code stays on P0302, you have just ruled out the most common ignition components without spending a single dollar. You have now moved the diagnostic focus to fuel injectors or mechanical compression. Historical trends in U.S. automotive repair suggest that 50% of misfire codes on vehicles with over 100,000 miles are actually caused by vacuum leaks, unmetered air, entering the engine through a cracked rubber hose or a failing intake manifold gasket. To find these, professionals use a smoke machine, but in a pinch you can observe your fuel trims at idle versus 3,000 RPM. If the fuel trims are high at idle but return to normal when you rev the engine, you have a vacuum leak. Why? Because at idle, the throttle plate is closed, creating high vacuum that sucks air through any tiny crack. When you open the throttle, the engine sucks in so much air through the main intake that the tiny leak becomes a negligible percentage of the total air mass. This is the kind of logical deduction that separates a parts changer from a technician. As we move into the next phase of this masterclass, we have to address the physical reality of the engine's mechanical health. No amount of sensor replacement can fix a car that has low compression or a jump timing chain. Modern engines in 2026 often use variable valve timing, or VVT, which relies on oil pressure to physically move the camshafts. A tiny bit of sludge from an overdue oil change can clog the VVT solenoid, causing the car to behave as if the entire engine is out of sync. We have established how the brain thinks and how it uses sensors to adjust the fuel mixture. We've looked at the hidden data of fuel trims and how they reveal a struggle before the light even flashes. But there is a silent killer that no sensor can directly measure, a force that can destroy an engine from the inside out while the computer thinks everything is perfectly fine. It involves the very lifeblood of the machine, and if you don't know how to read the physical signs of its degradation, you are missing half the story. In the next part, we are going to dive into the world of fluid dynamics and thermal management. We will explore why your temperature gauge on the dash is often lying to you, how to detect a head gasket failure before your engine turns into a boat anchor, and the specific chemical test that can save you $5,000 in engine replacement costs. Are you ready to see what the computer is hiding from you? Because the real secrets aren't just in the wires. They are in the oil, the coolant, and the very metal of the block itself. To begin this deep dive into the thermal lifeblood of your vehicle, we must first confront an uncomfortable truth in the world of automotive engineering. Your dashboard temperature gauge is almost certainly lying to you. In the year 2026, manufacturers have perfected the use of buffered gauges, often referred to by technicians as dummy gauges. Imagine a driver named Sarah, who is navigating her 2022 SUV through a heat wave in Phoenix. Sarah keeps a close eye on her needle, which stays perfectly centered, giving her a sense of security. However, if Sarah were looking at the raw data from the engine coolant temperature sensor through a professional scan tool, she would see the temperature fluctuating between 195 and 230 degrees Fahrenheit. The needle does not move because manufacturers found that small, normal fluctuations caused unnecessary panic for the average driver. The needle is programmed to stay in the middle until the temperature reaches a critical threshold, often around 240 degrees, at which point it spikes into the red. By then, the potential outcome is already severe. The aluminum cylinder head has likely begun to expand at a different rate than the engine block, risking a warped mating surface. Understanding the cooling system requires looking at it as a pressurized thermal exchange network. Modern engines are designed to operate at higher temperatures than those of 20 years ago to improve fuel atomization and reduce emissions. To prevent the coolant from boiling at these higher temperatures, the system is pressurized, typically to about 15 pounds per square inch. This pressure raises the boiling point of the fluid by about 3 degrees for every pound of pressure. If your radiator cap has a failing seal, the system cannot hold pressure, and your car will boil over at a temperature it should normally handle with ease. Historical trends in repair data suggest that a significant number of overheating cases are solved by replacing a $5 plastic cap rather than a $500 radiator. Let us look at a case study involving a mysterious overheating issue that Sarah might encounter. Her car only overheats while sitting at a red light, but cools down once she reaches highway speeds. To a diagnostic master, this is a massive clue. At highway speeds, the movement of the car forces air through the radiator fins. At a red light, the engine relies entirely on the electric cooling fans. If Sarah turns on her air conditioning and the fans do not immediately engage, she has identified a failure in the fan motor, the relay, or the fan control module. This is the logic of fluid dynamics. The heat has been moved from the engine to the coolant, but the coolant cannot move that heat to the atmosphere without airflow. However, the most feared word in automotive diagnostics is the head gasket. The head gasket is the critical seal between the engine block, where the pistons move, and the cylinder head, where the valves and spark plugs live. It must seal combustion pressure reaching thousands of pounds per square inch, while simultaneously keeping engine oil and coolant from mixing. When a head gasket fails, it can fail in several distinct ways, each with its own signature. Imagine if Sarah notices white, sweet-smelling smoke billowing from her exhaust. This is a sign that coolant is being sucked into the combustion chamber and burned. If she notices a milky, tan substance on her oil dipstick, often described as looking like a chocolate milkshake, it means coolant is leaking into the oiling system. This is an emergency. Coolant is an excellent heat exchanger but a terrible lubricant. If that mixture reaches the engine bearings, the metal-on-metal friction will destroy the engine in a matter of miles. To diagnose a failing head gasket without tearing the engine apart, we use the combustion leak test, also known as a block test. This is a masterclass level technique that uses chemistry to find what the eyes cannot see. You use a plastic chamber filled with a special blue fluid, which is placed over the radiator neck. As the engine runs, any air bubbles coming out of the coolant pass through this fluid. If there is a crack in the cylinder head or a breach in the gasket, carbon dioxide from the combustion process will enter the cooling system. When CO2 hits the blue liquid, which is typically a bromothymol blue solution, it reacts with the water to form carbonic acid, which lowers the pH and turns the liquid from blue to yellow or green. This is definitive proof of an internal engine failure. It is a scientific case study happening in the palm of your hand. We must also discuss the chemistry of the coolant itself. In 2026, you cannot simply go to a gas station and buy any jug of green fluid. Modern vehicles use specific formulations like organic acid technology or hybrid organic acid technology. These contain specialized corrosion inhibitors designed for the specific alloys in your engine. Historical data shows that mixing green IAT coolant with orange OAT coolant can lead to a chemical reaction called precipitation, where the additives fall out of the solution and create a thick, silicate sludge. This sludge clogs the tiny passages in your heater core, which is often the highest and most restricted point in the system. If you lose heat in your cabin during the winter, it is frequently a diagnostic sign that your cooling system is either low on fluid or contaminated with this gel-like sludge. Moving to the engine's oil, we find the primary diagnostic window into mechanical wear. Oil is the only thing that actually touches every moving part of the engine. When you perform an oil change, you should never just pour the old oil away. Professionals look for the shimmer of metallic flakes. A light silver shimmer suggests aluminum wear, possibly from a timing chain guide. A bronze or copper shimmer is far more serious, as it indicates the engine is eating into its main bearings. In 2026, many high-mileage drivers use oil analysis services. They send a small sample to a lab that uses mass spectrometry to identify the exact parts per million of different metals. This allows for a predictive diagnostic approach where you can see a bearing failure coming 3 months before it happens. Step by step, the fluid inspection process should be your first ritual. Start with the engine cold. Check the coolant level in the overflow tank and the radiator itself. Look for the color and clarity. Next, pull the oil dipstick. It should be translucent and amber or dark brown. If it is pitch black and gritty, the oil has exceeded its ability to hold soot in suspension, and you are currently experiencing accelerated wear on your camshafts. Then look at the underside of the oil fill cap. A small amount of white foam can be normal in cold climates due to condensation, but a thick coating of beige sludge is a warning of an internal leak. Imagine if you could see through the metal of the engine while it was running. That is essentially what you are doing when you analyze these fluids. You are looking at the remnants of the mechanical struggle. If the oil smells like gasoline, it means your fuel injectors might be leaking or your piston rings are worn, allowing unburned fuel to wash down the cylinder walls. This thins the oil and ruins its ability to protect the engine. Every scent, every color change, and every drop in level is a data point in the masterclass of Auto Diagnostics. We have mastered the brain and the blood of the machine, but there is one system that remains a mystery to most: the drivetrain. It is the most complex mechanical assembly in the vehicle, involving hundreds of moving parts that must engage and disengage with millisecond precision. If the engine is the heart, the transmission is the nervous system that translates power into motion. Many people assume a transmission shutter means a $5,000 replacement is inevitable, but historical trends show that the reality is often much simpler and much more interesting. In the next part of our masterclass, we are going to unlock the secrets of the transmission, explore the phenomenon of the strawberry milkshake of death, and show you how to diagnose a shifting issue that most shops will tell you is impossible to fix. The world of gears and clutches is about to become a lot less intimidating. The transmission is the most misunderstood component in the automotive world, often treated as a mysterious black box that either works or requires a $5,000 replacement. In reality, the modern automatic transmission is a masterpiece of hydraulic logic and electronic oversight. To understand it, you must stop thinking of it as a set of gears and start thinking of it as a series of fluid-controlled switches. In 2026, even a standard commuter vehicle might have an 8, 9, or 10-speed transmission. Each of those gears represents a specific combination of planetary gear sets being held still or allowed to spin by hydraulic clutches and bands. If the engine control module is the conductor, the transmission control module or TCM is the choreographer, ensuring that every shift happens with millisecond precision to balance fuel economy with power delivery. Let us explore the phenomenon known in the technician community as the strawberry milkshake of death. This is a catastrophic failure that occurs when the internal wall of the transmission cooler, which is usually located inside the engine's radiator, fails. Imagine Marcus, a father in suburban Ohio, driving his family's 2018 minivan in the year 2026. He notices the transmission starting to slip and hesitating between gears. When he pulls the transmission dipstick, he doesn't see the bright, translucent red of healthy automatic transmission fluid. Instead, he sees a thick, frothy pink substance that looks exactly like a strawberry milkshake. This is a chemical nightmare. The engine coolant has breached the transmission lines. Because the friction material on the internal clutch plates is often paper-based and held together by water-soluble adhesives, the presence of coolant literally dissolves the clutches. Historical trends show that once this mixture has circulated for more than a few miles, the potential outcome is a total transmission overhaul. This case study highlights why a routine visual inspection of your fluids can save the entire vehicle. If Marcus had spotted a slightly cloudy look to his coolant in the overflow tank a month earlier, he might have caught the radiator failure before it cross-contaminated the drivetrain. Beyond catastrophic fluid mixing, the most common transmission complaint in the US involves the shudder. Imagine if you are driving at 45 miles per hour and it feels like you just ran over a series of small rumble strips, yet the road is perfectly smooth. This is often the torque converter clutch or TCC shudder. The torque converter is the fluid coupling between the engine and the transmission. To improve fuel efficiency at cruising speeds, a small internal clutch locks the two together so there is no fluid slip. If the fluid is degraded or the friction modifiers have worn out, this clutch will rapidly grab and release, creating that vibration. A diagnostic masterclass technique involves the brake tap test. While maintaining a steady speed and feeling the shudder, lightly touch the brake pedal with your left foot, just enough to trigger the brake lights but not enough to slow the car. This tells the TCM to disengage the TCC. If the vibration instantly vanishes, you have successfully isolated the problem to the torque converter, potentially avoiding a misdiagnosis of a failing engine or an out-of-balance tire. We must also discuss the role of the shift solenoid. These are the actuators we mentioned in the previous part. They are electromagnetic valves that open and close to direct pressurized fluid into the various clutch packs. If Marcus's minivan suddenly loses second gear but has every other gear, it is highly unlikely that the entire transmission has failed. Instead, a specific solenoid has likely failed electrically or become clogged with a tiny fragment of metal. In 2026, the TCM is incredibly sensitive to these electrical signatures. If the computer detects that a solenoid is drawing too much or too little amperage, it will trigger a P0700 series code and often put the car into limp home mode. This is a protective state where the transmission stays in a single gear, usually third, to prevent further mechanical damage. Understanding that an electronic part the size of a pill can disable a 3-ton vehicle is the first step toward avoiding unnecessary mechanical teardowns. For many modern drivers, the experience of a continuously variable transmission or CVT is the new norm. Unlike a traditional automatic, a CVT uses 2 pulleys and a steel belt to provide an infinite range of gear ratios. While efficient, they have unique failure modes. Historical data from the mid-2020s indicates that heat is the primary enemy of the CVT belt. When the belt begins to slip on the smooth pulley surfaces, it creates micro-scratches. This leads to a rubber band sensation where the engine revs up, but the car doesn't seem to gain speed proportionally. If you are diagnosing a CVT, you are looking for specific data in the scan tool called secondary pressure. If the pressure isn't high enough to clamp that belt, the transmission is essentially eating itself. The step-by-step fluid analysis is your primary diagnostic tool here. First, understand that many modern cars are sealed for life, meaning they have no dipstick. To check these, you must use a fill plug on the side of the transmission case while the fluid is at a very specific temperature, usually between 100 and 120 degrees Fahrenheit. This requires a scan tool to monitor the live transmission temperature. If the fluid is black and smells like burnt toast, the friction material has already begun to burn. In this scenario, historical trends suggest that a high-pressure transmission flush can actually be detrimental. The dark fluid often contains suspended friction material that is actually helping the worn clutches grab. Replacing it all at once with slippery new fluid can cause a worn transmission to start slipping immediately. This is why a simple pan drop and filter change is often the safer path for high-mileage vehicles. Another layer of the diagnostic masterclass is the concept of adaptive learning. The TCM monitors how long it takes for a shift to complete. As the clutches wear down and become thinner, the piston has to travel further to apply pressure. The TCM learns this and begins to apply the fluid slightly earlier, or with more pressure to maintain a smooth feel. If you replace a transmission or even just some internal parts, you must perform an adaptive reset. If you don't, the computer will try to operate the new, tight parts with the old, aggressive pressure settings, which can lead to harsh shifts or even mechanical failure within a few hundred miles. We have moved from the brain of the car to the lifeblood of the engine and now through the complex hydraulic logic of the drivetrain. You are starting to see the vehicle not as a single object, but as a series of overlapping systems that must stay in perfect synchronization. However, even the most mechanically sound engine and the most perfectly shifting transmission are useless if the invisible force that powers them begins to fail. In 2026, the most frequent reason for a vehicle to be towed is not a mechanical breakdown, but an electrical ghost. The electrical system is the most feared territory for the DIY mechanic, but it follows the most rigid and predictable laws of physics. In the next part, we are going to demystify the battery, the alternator, and the dreaded parasitic draw. We will show you how to find a short circuit using nothing but a light bulb, why a bad ground wire can make your dashboard light up like a Christmas tree, and how to tell if your battery is actually dead, or if your car is simply being robbed of its power while you sleep. The invisible world of electrons is about to become visible. To master the electrical system of a modern vehicle in 2026, you must first abandon the idea that electricity is a mysterious force. It is the most logical system in your car because it follows the rigid laws of physics, specifically Ohm's law, without exception. Think of electricity like water flowing through a pipe. Voltage is the pressure, current or amperage is the flow rate, and resistance is the size of the pipe. When your car develops an electrical ghost, it is simply a case of pressure being lost, flow being restricted, or water leaking where it shouldn't. In the United States, electrical issues account for nearly 20% of all non-collision repair orders, yet they are the most frequently misdiagnosed problems because people tend to replace parts before they measure the circuit. Let us look at the foundation, the battery. In 2026, the traditional lead-acid battery has largely been replaced by absorbed glass mat or AGM technology in most high-end and mid-range vehicles. These batteries are more resilient, but they are also more sensitive to charging parameters. Imagine Jordan, a graphic designer in Seattle, who wakes up to find their 2024 sedan completely dead. Jordan jumps the car, drives to a big box store, and buys a new battery. However, within 2 weeks, the new battery is dead again. Jordan assumes the new battery was defective, but the historical trends of modern vehicles suggest a different culprit: the battery management system, or BMS. In the year 2026, your car does not just blindly charge the battery. The ECM monitors the age and internal resistance of the battery and adjusts the alternator's output accordingly. When Jordan replaced the battery without performing a battery registration through a scan tool, the car still thought it was charging a 3-year-old, degraded battery. It likely overcharged the new AGM unit, causing internal off-gassing and premature failure. This is a crucial masterclass step. On modern US vehicles, the battery is no longer a plug-and-play component. It is a data point that must be updated in the computer's registry. Now, let us move to the alternator, which is the actual power plant of the vehicle. In older cars, you could check an alternator by simply seeing if it put out 14 volts. In 2026, that is no longer a valid test. Modern alternators are pulse width modulated, meaning the ECM tells the alternator exactly when to turn on and off to save fuel. If you are cruising on a highway and your battery is fully charged, The ECM might command the alternator to drop its output to 12.8 volts to reduce the mechanical load on the engine. A technician who doesn't understand this might see 12.8 volts and tell you that your alternator is failing, when in reality, it is performing perfectly. To diagnose this, you must use a scan tool to look at the alternator duty cycle. If the computer is commanding 90% output but the voltage is dropping, then you have a verified failure. The most frustrating electrical issue for any driver is the parasitic draw, the silent thief that drains your battery while the car is parked. Imagine if Jordan's car wasn't a battery registration issue, but instead, a module that refused to go to sleep. Modern cars have dozens of modules that should enter a low-power sleep mode about 20 minutes after the ignition is turned off. If a single module, like the telematics unit or a door lock sensor, stays awake, it can pull 500 milliamps of current. Over a single night, that is enough to prevent a car from starting. The historical method for finding a draw was to pull fuses one by one while watching an ammeter. In 2026, we do not do this. Pulling a fuse can wake up the entire data bus, resetting the fault and making it impossible to find. Instead, we use the millivolt drop method. Every fuse has a tiny amount of internal resistance. If current is flowing through a fuse, there will be a measurable drop in voltage across the two small test points on the top of the fuse. By using a digital multimeter set to millivolts, you can touch the probes to the top of each fuse. You then consult a standardized chart that converts that millivolt reading into a milliamp draw based on the fuse's rating. This allows you to identify exactly which circuit is staying active without ever breaking the circuit or waking up the car's computers. We must also address the most common cause of the Christmas tree dashboard, where multiple unrelated warning lights, ABS, airbag, and traction control, all illuminate at once. This is almost never a case of all those systems failing simultaneously. Instead, it is usually a sign of a bad ground. In the US, where road salt and humidity can lead to rapid corrosion, the ground straps that connect the engine and the body to the negative terminal of the battery are critical. Electricity must complete a full circle to work. If the path back to the battery is restricted by rust, the voltage will find an alternative path through other sensors, backfeeding them and causing the ECM to see implausible signals. A diagnostic masterclass technique for finding these hidden bottlenecks is the voltage drop test. This is far superior to a simple continuity or resistance test. While the circuit is under load, for example while cranking the engine, you place one probe of your multimeter on the negative battery post and the other on the engine block. In a perfect world, the reading should be nearly zero. If you see a reading of 0.5 volts or higher, it means the electricity is struggling to get through that connection. You have found a high resistance point that is acting like a dam in your water pipe. This simple 5-minute test can save a driver from replacing a perfectly good starter motor or ECM. Consider the case study of a 2022 pickup truck that suffered from a random stalling issue. The owner had already replaced the fuel pump and the crank position sensor. By performing a voltage drop test on the main power relay, a technician discovered that the internal contacts of the relay were pitted. Under the heat of operation, the resistance increased until the voltage dropped low enough that the fuel pump simply stopped spinning. A $12 relay was the fix, but it was only found by measuring the pressure of the electrical flow, while the system was actually working. As we move deeper into the digital age of 2026, the complexity of these circuits is only increasing. We are no longer just dealing with 12-volt power wires. We are dealing with high-speed data lines that carry information in the form of voltage square waves. If a power wire is a pipe, a data line is a fiber optic cable. You cannot test a data line with a test light, as the tiny amount of current drawn by the bulb can actually fry the sensitive communication chips in the vehicle's modules. Understanding the barrier between power circuits and logic circuits is what separates the modern technician from the hobbyist. We have now covered the brain, the fluids, the drivetrain, and the nervous system of your vehicle. You are beginning to see how these systems are intertwined. A failure in the electrical system can mimic a mechanical failure, and a mechanical failure can trick a sensor into reporting an electrical fault. But there is one area where all these systems meet, and it is the most critical for your safety and the longevity of your tires. It is the world of chassis dynamics and the sensors that monitor your contact with the road. In the next part, we are going to explore the invisible forces of alignment, the science of electronic stability control, and why a tiny sensor in your steering wheel might be the reason your car feels like it's fighting you on every turn. The mystery of the wobble and the pull is about to be solved. To solve the mystery of the wobble and the pull, we have to look at your vehicle not as a rigid block of steel, but as a dynamic, flexible geometry that is constantly fighting against the forces of friction and gravity. In 2026, the chassis of a car is more than just a frame. It is a sensitive network of sensors that monitor every degree of rotation and every pound of force. If your steering wheel is off-center or your car is drifting toward the shoulder of the highway, it is not just an annoyance. It is a data mismatch that can confuse your vehicle's safety systems. Let us introduce Taylor, a commuter in Chicago who drives a 2024 mid-sized sedan. After a particularly harsh winter that left the city streets riddled with deep potholes, Taylor noticed that the car started to pull slightly to the right. More concerningly, the traction control light would flicker briefly during perfectly dry, straight-line acceleration. Taylor assumed the tires were just worn, but the reality was a complex failure of both mechanical alignment and electronic calibration. To understand Taylor's situation, we must perform a deep dive into the three pillars of wheel alignment: toe, camber, and caster. Historical trends in automotive service show that these are the most frequently ignored aspects of preventative maintenance, yet they dictate the potential outcomes for tire longevity and fuel efficiency. Toe is the most critical angle for tire wear. Imagine standing up and looking down at your feet. If you point your toes toward each other, you are toe in. If you point them away, you are toe out. In a car, toe in provides stability, while toe out can make a car feel more eager to turn but also more darting and nervous. When Taylor hit a pothole, the force likely bent a tie rod, the mechanical link between the steering rack and the wheel, causing a massive toe-out condition on the right side. This created a scrub effect where the tire was essentially being dragged sideways while moving forward. Historical data suggests that even a fraction of an inch of incorrect toe can be equivalent to dragging your tire sideways for 100 miles over the course of a 1,000-mile trip. Camber is the vertical tilt of the wheel. If the top of the wheel leans in toward the engine, it is negative camber. If it leans out, it is positive camber. While performance cars use negative camber to improve grip in corners, excessive camber on a daily driver causes the inside or outside edge of the tire to bald prematurely. Caster is the most misunderstood of the three. It is the angle of the steering pivot when viewed from the side, much like the front forks of a bicycle. Positive caster is what makes your steering wheel return to the center after a turn. It provides that straight-ahead stability you feel on the interstate. If your caster is uneven from left to right, the car will pull toward the side with the least amount of positive caster. However, in 2026, a mechanical alignment is only half the battle. This is where Taylor's traction control light comes into play. Modern vehicles are equipped with the steering angle sensor, or SAS. This sensor is located behind the steering wheel and tells the computer exactly where the driver is pointing the car. In Taylor's case, because the tie rod was bent, Taylor had to hold the steering wheel at a 5-degree angle to the left just to keep the car going straight. The computer, however, saw that the wheels were moving at equal speeds, indicating a straight line, while the SAS reported a 5-degree turn. This is what we call an implausible signal. The electronic stability control, or ESC module, became confused. It thought the car was sliding or understeering, and it began to pulse the individual brakes to correct a skid that wasn't actually happening. This is why Taylor saw the traction control light. The fix wasn't just a new tie rod and a mechanical alignment. It required a SAS recalibration to tell the brain that the new center was actually 0 degrees. Now let us address the wobble. If you feel a vibration in your seat, the problem is likely in the rear of the vehicle. If you feel it in the steering wheel, it is in the front. But we must distinguish between a high-speed shake and a death wobble. A shake at 60 miles per hour is almost always a wheel balance issue. A tiny lead weight may have fallen off your rim, causing a centrifugal imbalance. But a wobble that occurs specifically when you hit a bump, especially in trucks and SUVs, is often a sign of worn-out suspension joints. Imagine if your arm was held into your shoulder socket by a loose rubber band. That is what a failing ball joint or control arm bushing feels like. When the tire hits a bump, the energy causes the wheel to oscillate uncontrollably because the mechanical dampening is gone. Step by step, you can diagnose this with the 12-in-6 and 9-in-3 test. With the car safely on jack stands, grab the tire at the top and bottom and try to rock it. If there is play, your ball joints or wheel bearings are failing. If there is play when you rock it from side to side, your tie rods are the culprit. Another diagnostic masterclass tip involves the radial pull. Sometimes a car pulls to one side even when the alignment is perfect. This is caused by a manufacturing defect or internal damage to the tire's steel belts, known as tire conicity. To diagnose this, simply swap the two front tires. If the car now pulls in the opposite direction, you have scientifically proven that the problem is the tire, not the car. This prevents you from spending hundreds of dollars on alignment racks when the solution is simply a new set of rubber. We must also look at the role of the wheel speed sensors, or WSS. These are small magnetic sensors located at each wheel hub. In 2026, they do more than just manage anti-lock braking systems. They provide the data for everything from your speedometer to your hill start assist. A common case study involves a driver who sees an ABS light and finds that their cruise control also stops working. This is because the computer can no longer trust the vehicle's speed data. Often, these sensors aren't broken. They are just dirty. Because they are magnetic, they attract metallic dust from the brake pads. Cleaning the tip of a WSS can often restore the entire system's functionality. Imagine if you were walking on a sheet of ice. You would use your inner ear for balance and your feet to feel the grip. Your car does the same. The yaw rate sensor acts as the inner ear, measuring the vehicle's rotation, while the WSS act as the feet. When these are in sync, the car can perform incredible feats of safety, like braking a single inner wheel to prevent a rollover. But when the alignment is out of sync, the inner ear and the feet start telling different stories, leading to a vehicle that feels twitchy, unsafe, and unpredictable. We have now demystified the brain, the blood, the nervous system, and the skeletal structure of your vehicle. You are beginning to see how a physical dent in a metal bar can lead to a digital error in a computer's memory. But all of this movement requires energy, and that energy comes from a process that is becoming increasingly scrutinized and complex: the combustion cycle and the management of the air we breathe. While the chassis keeps you on the road, the engine's breathing determines if you can stay on that road without the authorities or the environment stopping you. In the next part of this masterclass, we are going to dive into the black magic of the intake and exhaust systems. We will explore the secret life of the turbocharger, the reason why your car might be choking on its own exhaust gases through a failing EGR valve, and how to use a simple vacuum gauge to see deep inside the combustion chamber without ever turning a wrench. The air your car breathes is about to become your next diagnostic superpower. To understand the respiratory system of your vehicle, you must envision the engine as a massive air pump. For every gallon of gasoline your car consumes, it must breathe in approximately 9,000 gallons of air. In the year 2026, this process has become incredibly refined through the use of forced induction and complex manifold geometries. Imagine Derek, a delivery driver in Atlanta, navigating the humid afternoon traffic in a 2023 turbocharged sedan. Derek notices that when he merges onto the highway, the engine produces a high-pitched whistling sound, followed by a sudden loss of power that feels as if the car has hit an invisible wall. This is a classic case study in atmospheric management, and to diagnose it, we have to follow the path of the air from the atmosphere to the tailpipe. The journey begins at the air filter, but the real complexity starts at the turbocharger. In 2026, small displacement turbocharged engines are the standard in the United States because they offer the potential outcomes of high fuel efficiency during cruising and high power during acceleration. A turbocharger uses the wasted energy of the exhaust gases to spin a turbine, which in turn spins a compressor wheel that forces more air into the engine. If Derek hears a whistle, he is likely hearing a boost leak. This occurs when a rubber coupler or a plastic intake pipe has developed a crack. Under the high pressure of the turbo, often reaching 20 pounds per square inch, the air is forced out of the crack, creating a siren-like sound. Because this air has already been measured by the mass airflow sensor, the computer has already added the fuel for it. When the air escapes before reaching the cylinders, the engine runs extremely rich, potentially leading to black smoke and fouled spark plugs. To diagnose this step by step, a technician uses a boost leak tester, which is essentially a plug that allows you to pressurize the intake system with an air compressor while the engine is off. By spraying soapy water on the hoses, you can find the bubbles that reveal the leak. But Derek's problem could also be internal to the turbo. If the wastegate, the valve that regulates boost pressure, becomes stuck, the turbo can overboost. The computer detects this through the manifold absolute pressure or MAP sensor and immediately enters a limp mode to prevent the engine from literally blowing its gaskets. This is the invisible wall Derek felt. It is a protective software intervention based on a mechanical failure. As the air moves into the intake manifold, it encounters another 2026-era challenge: carbon buildup. Most modern vehicles use gasoline direct injection or GDI. In older port-injected engines, the fuel was sprayed onto the back of the intake valves, which acted as a solvent to keep them clean. In a GDI engine, fuel is sprayed directly into the combustion chamber. This means the intake valves never get washed. Over time, oil vapors from the crankcase combine with heat to bake a hard, carbon crust onto the valves. Imagine if you tried to breathe through a throat partially blocked by a thick layer of wool. Historical trends show that by 60,000 miles, many GDI engines experience a significant restriction in airflow. This manifests as a rough idle or a cold start stumble. To diagnose this without taking the engine apart, we use a borescope, a tiny camera, threaded through the intake sensor ports to visually inspect the choking of the valves. Now we must discuss the exhaust gas recirculation or EGR system. This is the part of the car that makes it eat its own smoke. To reduce nitrogen oxide emissions and lower combustion temperatures, the EGR valve opens to allow a small amount of inert exhaust gas back into the intake manifold. Imagine if Derek's EGR valve becomes stuck in the open position. At a red light, the engine needs pure, oxygen-rich air to stay idling. If the valve is stuck open, the engine is fed a diet of oxygen-poor exhaust, causing it to stall. If you have a car that runs great on the highway but dies the moment you come to a stop, the EGR valve is your primary suspect. To see deep into the health of the combustion chamber without a camera, we return to a tool that has remained unchanged for 100 years, the vacuum gauge. Even in 2026, the physics of vacuum remains the most honest indicator of engine health. You connect the gauge to a port on the intake manifold and observe the needle. A healthy engine at sea level should hold a steady 19 to 21 inches of mercury at idle. If the needle is vibrating rapidly, it suggests worn valve guides or a burnt valve that isn't sealing. If the needle drops steadily as you hold the engine at a constant 2000 RPM, you have found a restricted exhaust. This brings us to the final stage of the journey, the catalytic converter. This is a chemical laboratory inside a stainless steel can. It uses precious metals like platinum, palladium, and rhodium to convert toxic gases into water vapor and carbon dioxide. However, the converter is a passive observer. It can only process what the engine gives it. If Derek ignores a misfire for 6 months, the unburned raw fuel travels down the exhaust and hits the red-hot honeycomb of the converter. The fuel ignites on contact, raising the internal temperature to over 2000 degrees. This causes the ceramic substrate to melt, turning the converter into a solid plug. Now the engine can no longer exhale. This creates back pressure that can be measured by removing the upstream oxygen sensor and installing a pressure gauge. Anything over 2 pounds of back pressure at idle indicates a failing exhaust system. The dreaded P0420 code, catalyst efficiency below threshold, is the car's way of saying the laboratory is no longer working. But a masterclass student knows to check the oxygen sensors first. The upstream sensor before the cat should be rapidly switching between high and low voltage as it monitors the fuel mixture. The downstream sensor after the cat should be a steady, flat line, indicating that the oxygen has been used up in the chemical conversion process. If the downstream sensor is mimicking the upstream sensor, you know the catalyst is dead. We have explored the intake, the compression of air through the turbo, the recycling of gases through the EGR, and the final treatment in the exhaust. You now understand that a car's breathing is a delicate balance of pressure, temperature, and chemistry. When one part of this loop fails, the symptoms can ripple across the entire vehicle, making an exhaust problem look like a transmission slip or a turbo failure look like a dead battery. But as we look at the car as a whole, there is one more layer of communication we haven't touched. It is the language of safety and stability. Your car is constantly monitoring the friction between your tires and the pavement, and it is prepared to take control of the brakes and the steering in a split second to save your life. In the next part of this series, we are going to dive into the world of anti-lock braking systems, electronic stability control, and the high-tech sensors that live inside your wheels. We will explore why a tiny piece of road debris can disable your entire safety suite, and how to diagnose the phantom brake syndrome that has become a major case study in modern automotive safety. The path to the contact patch starts now. The path to the contact patch begins with a fundamental understanding of how your car maintains its grip on reality. In 2026, the 4 patches of rubber touching the asphalt are the only things standing between a controlled commute and a chaotic kinetic event. To manage this, your vehicle uses the anti-lock braking system, or ABS, as its primary sensory network. While most drivers think of ABS as just a tool to prevent skidding during a panic stop, it has evolved into the foundation for almost every modern safety feature, from traction control to electronic stability control, and even autonomous emergency braking. When this system fails, it doesn't just lose the ability to pulse the brakes, it loses its sense of touch. Let us look at the primary witness in this system: the wheel speed sensor. Imagine Carlos, a delivery professional in Pennsylvania, driving a 2024 heavy-duty van in the spring of 2026. The roads are a mess of melting slush and hidden debris. Suddenly, Carlos feels a strange vibration in the brake pedal, almost like a grinding sensation, even though he is barely slowing down for a stop sign on a dry patch of road. Then the ABS, traction control, and stability lights all illuminate simultaneously. This is the classic symptom of a failing wheel speed sensor or a compromised tone ring. To diagnose this, we must understand the two types of sensors used in 2026. Historical trends show a shift from passive sensors to active sensors. A passive sensor is essentially a magnet wrapped in wire. As a notched steel ring called a tone ring spins past the sensor, it creates a small alternating current voltage. The computer counts these pulses to determine how fast the wheel is spinning. An active sensor or Hall effect sensor is far more sophisticated. It receives a reference voltage from the computer and produces a digital square wave signal. These are much more accurate at low speeds, which is why your 2026 vehicle can perform smooth low-speed maneuvers like traffic jam assist. In the case study of Carlos, the potential outcome was determined by a single piece of road salt. Over time, salt and moisture can get behind a pressed-on tone ring, causing it to rust and expand. This is known as rust jack. As the ring expands, it can actually crack, or it can move just far enough away that the sensor loses its read. When Carlos was slowing down, the cracked tone ring created an irregular gap in the pulses. The computer saw 3 wheels spinning at 5 miles per hour, and 1 wheel suddenly dropping to 0 miles per hour for a fraction of a second. The computer reacted logically. It assumed that 1 wheel had locked up on ice and immediately began to pulse the ABS solenoids to release pressure. This is the phantom brake syndrome. The car is trying to save you from a skid that isn't actually happening. Step by step, diagnosing this requires looking at live data. You don't need to be a scientist to see the fault. By using a scan tool while a passenger drives the car at a slow, steady speed, you look at the speed of all 4 wheels. If 3 wheels show 5 miles per hour and the 4th wheel is flickering between 5 and 0, you have isolated the problem. But the masterclass technique is to look at the sensor's mounting surface. Often, the sensor itself is fine, but rust has pushed it upward, increasing the air gap between the sensor tip and the tone ring. Filing down the rust on the mounting surface to bring the sensor closer can often restore the signal without buying a single new part. However, the ABS system is only half of the stability story. We must also discuss the yaw rate sensor and the lateral accelerometer. If the wheel speed sensors are the feet of the car, the yaw rate sensor is the inner ear. It is usually located in the very center of the vehicle, often under the center console because that is the pivot point. It measures how fast the car is rotating around its vertical axis. Imagine if Carlos enters a turn too fast on a wet road. His steering wheel is turned 20 degrees to the left, but the yaw rate sensor reports that the car is not rotating. This is understeer. The electronic stability control module immediately realizes the car is sliding straight. In a millisecond, it applies the brake to the inside rear wheel. This creates a drag that physically pulls the nose of the car back into the turn. In 2026, the complexity increases as these systems integrate with the Advanced Driver Assistance Systems, or ADAS. Your car now has eyes, cameras behind the rearview mirror, and radar sensors behind the front grille. These systems are networked with the ABS module. If the camera sees a car stopping abruptly ahead, it sends a high-priority request to the ABS hydraulic control unit to prime the brakes. It moves the brake pads closer to the rotors so that the moment you touch the pedal, the response is instantaneous. This brings us to a significant diagnostic challenge: ADAS calibration. If you have your windshield replaced or your car is involved in a minor fender bender that shifts the front bumper by just a few millimeters, the eyes of the car might be looking at the ground or the sky instead of the road. Historical data suggests that many intermittent braking issues are actually caused by misaligned radar sensors. The car sees a metallic sign on the side of a curve and misinterprets it as a stationary vehicle in its path, leading to a sudden jarring autonomous braking event. Diagnosing this requires checking the alignment angle data in the ADAS module. We must also address the physical side of the braking system. While the electronics are the brains, the hydraulics are the muscle. Brake fluid is hygroscopic, meaning it actively absorbs moisture from the air. In a humid U.S. climate, your brake fluid can reach a 2% water content in as little as 2 years. Under heavy braking, that water turns into steam. Unlike liquid, steam is compressible. This leads to a spongy pedal. But more importantly for our diagnostic masterclass, that moisture causes internal corrosion in the ABS hydraulic control unit. There are tiny valves inside that unit, thinner than a human hair, that must move at lightning speed. If they become sticky due to old, contaminated fluid, the ABS light will trigger a pump motor circuit or valve failure code. This is a $3,000 lesson in the importance of a $40 fluid flush. As we look at the contact patch, we see that the machine is a constant conversation between mechanical grip and electronic oversight. You have learned how to hear the chatter of a failing tone ring and how to interpret the confusion of a yaw sensor. You understand that when your dashboard lights up, the car isn't just complaining. It is telling you exactly which part of its sensory network has gone dark. But there is a system even more vital to the pulse of the vehicle, one that deals with extreme pressures and the very energy that makes movement possible. It is a system that can fail silently, slowly robbing you of power and efficiency until one day, the car simply refuses to wake up. We are talking about the high-pressure world of fuel delivery and the secrets hidden within the fuel rails and the combustion injectors. In the next part, we are going to dive into the chemistry of combustion, the diagnostic signs of a lazy fuel pump, and why the gas you choose in 2026 might be the reason your engine is slowly starving to death. The fuel loop is about to be cracked open. The fuel loop is a masterpiece of chemistry and pressure that operates under conditions so extreme, they would have been unthinkable in a mass-produced vehicle just 2 decades ago. In 2026, the standard for fuel delivery in the United States is the dual injection system, which combines the benefits of port fuel injection for low-load cleanliness and gasoline direct injection, or GDI, for high-load power and efficiency. To understand why your car is struggling, you have to realize that it is balancing 2 entirely separate fuel circuits. One operates at a modest 60 pounds per square inch, while the other, the high-pressure side, can reach staggering pressures of over 3,000 pounds per square inch. When one of these systems falters, the symptoms can be as subtle as a slight drop in fuel economy, or as dramatic as a total engine stall at highway speeds. Let us look at the case study of Mia, a healthcare professional in California who drives a 2024 hybrid sedan. Mia's car has begun to experience what technicians call a long crank condition. Every morning, instead of the engine firing up instantly, it turns over for 5 or 6 seconds before stumbling to life. To a masterclass student, this is a glaring signal. In 2026, fuel systems are returnless and designed to hold pressure, even when the engine is off. Inside the fuel tank, the low-pressure fuel pump contains a one-way check valve. Its only job is to prevent the fuel in the lines from draining back into the tank when you turn the key off. Mia's check valve has developed a microscopic leak. Over several hours of sitting, the pressure in the lines drops to 0. When she tries to start the car, the pump has to prime the entire length of the vehicle before a single drop reaches the injectors. This is a classic example of a mechanical failure that leaves no electronic trace. The computer sees a functional pump and a functional engine, so it may not even trigger a light. A simple step-by-step diagnostic involves using a fuel pressure gauge with a shutoff valve. By isolating the tank from the engine, you can see if the pressure drop is happening at the front or the back of the car. But what about the lazy fuel pump? This is a phenomenon that plagues many high-mileage vehicles in the US. A fuel pump is a DC motor, and like all motors, it creates heat. In modern vehicles, the fuel itself acts as a coolant for the pump. If a driver consistently runs their tank down to the low fuel warning light, the pump is no longer submerged in its cooling bath. Historical trends indicate that this leads to increased internal resistance. The pump begins to spin slower, and as it struggles to push fuel against the pressure regulator, it draws more electrical current. In our diagnostic masterclass, we don't just check if a pump is on, we perform an amperage draw test. By using an inductive amp clamp around the fuel pump wire, we can see the literal effort the pump is making. A healthy pump might draw 5 to 7 amps. A lazy pump might pull 12 amps. This high current is a predictor of a future failure. It tells us that the pump's internal brushes are wearing out or the commutator is pitted. By catching this early, you avoid the potential outcome of being stranded on a busy interstate during a 2026 summer heat wave. Now we must address the fuel itself. In 2026, the composition of gasoline in the United States has shifted toward higher ethanol blends, such as E15. Ethanol is an excellent octane booster, but it is also hygroscopic, meaning it attracts water from the atmosphere. If a vehicle sits for an extended period, a common scenario for recreational vehicles or secondary cars, the fuel can undergo phase separation. This is where the water and ethanol bond together and sink to the bottom of the tank, leaving a layer of low-octane, dead gasoline on top. Imagine a scenario where a car has been sitting for 3 months. The driver starts it up, and it runs terribly, knocking and pinging under any load. This isn't a mechanical failure. It is a chemical one. The engine is trying to run on the water-heavy layer at the bottom of the tank. To diagnose this, we look at the fuel trim data we discussed in previous parts. If the computer is adding 30% more fuel but the engine is still knocking, the energy density of the fuel is the problem. In 2026, some advanced scan tools can actually show you the calculated ethanol percentage. If the sensor says the fuel is 40% ethanol but you only filled up with E10, you know you have a water contamination issue. On the high-pressure side of the system, we deal with the GDI pump. This pump is not electric. It is mechanical, driven by a dedicated lobe on the camshaft. This is where precision becomes a matter of life and death for the engine. If the high-pressure fuel pump, or HPFP, develops an internal leak, it can leak raw gasoline directly into the engine's oiling system. This is an invisible killer. Imagine if Mia checked her oil and found the level had actually risen on the dipstick. This is a sign of oil dilution. The gasoline thins the oil, ruining its lubricity and potentially causing catastrophic bearing failure. A masterclass technician will always smell the oil dipstick. If it smells like a gas station, the HPFP is failing internally. The injectors themselves are the final gatekeepers. In 2026, we are seeing the rise of piezoelectric injectors. These don't use a slow electromagnetic coil. They use crystals that expand and contract instantly when electricity is applied. This allows for up to 5 separate injection events per single combustion stroke. We can diagnose a clogged injector by looking at the cylinder power balance. By using a scan tool to disable one injector at a time while the engine is running, we measure the drop in RPM. If disabling cylinder 3 causes a 500 RPM drop, but disabling cylinder 4 only causes a 50 RPM drop, we have proven that cylinder 4 was barely contributing any power. We have explored the heart of the fuel system, the chemical traps of modern gasoline, and the extreme pressures that drive 2026 performance. You now see the fuel loop not as a simple tank and line, but as a high-speed, pressurized delivery network that must be perfectly timed to the millisecond. If the pressure is off by even 5%, the entire symphony of combustion falls out of tune. We have now covered almost every major system of the vehicle: the brain, the blood, the skeleton, the nervous system, and the respiratory and circulatory loops. You have the tools to listen to what the car is telling you, to see the invisible data, and to predict failures before they happen. But there is one final piece to the puzzle. It is the culmination of all this data, the Total Vehicle Health Report. It involves the future of how we interact with these machines as they become even more autonomous and connected. In our final part, we are going to pull everything together to show you how to perform a professional-level pre-purchase or long-trip inspection that guarantees nothing is left to chance. We are also going to look at the emerging world of over-the-air diagnostics and how the car of the future might already be fixing itself before you even know it's broken. The masterclass is reaching its peak. The Total Vehicle Health Report is the culmination of every sensory input, digital bit, and mechanical rhythm we have discussed throughout this masterclass. In the year 2026, the car has evolved into a software-defined vehicle, but the physical laws of thermodynamics and friction remain unchanged. To pull these threads together, we must look at a high-stakes scenario. Imagine Chris, a young professional in Denver, who is standing in a used car lot looking at a 2023 turbocharged SUV. The paint is pristine, the interior smells new, and when Chris turns the key, there are no warning lights on the dashboard. To the average buyer, this is a perfect vehicle. But Chris is armed with the diagnostic mindset. Chris understands that in 2026, a clean dashboard can be an illusion. Historical trends in the used car market show that some sellers use handheld scanners to perform a global clear of all fault codes just minutes before a potential buyer arrives. This turns off the check engine light, but it does not fix the car. To expose the truth, Chris performs the first step of the ultimate diagnostic masterclass, checking the readiness monitors. Every OBD2 vehicle since the mid-90s has these internal self-tests. There are monitors for the catalyst, the evaporative system, the oxygen sensors, and the misfire detection. When you clear the codes, these monitors are reset to not ready. If Chris sees that 6 out of 8 monitors are incomplete, he knows the car's memory has been recently wiped. The car hasn't proven itself healthy. It is simply in a state of digital amnesia. Beyond readiness monitors, Chris dives into the world of permanent diagnostic trouble codes. This is a feature of the latest global diagnostic standards. Unlike traditional codes, a permanent DTC cannot be cleared by a scan tool or by disconnecting the battery. It can only be cleared by the car's own computer, after it successfully performs a drive cycle and verifies that the physical repair has been made. If Chris finds a permanent P0420 code for catalyst efficiency, he knows that the catalytic converter was failing very recently, regardless of the light being currently off. This single data point saves him from a potential outcome involving a $3,000 exhaust repair. To further validate the vehicle's health, we move into the Mode 6 data we teased earlier. This is the unedited, raw laboratory data of the engine. In 2026, scan tools can translate these hexadecimal values into plain English. Chris looks at the misfire counts for each individual cylinder over the last 10 drive cycles. Even if the car is currently running smooth, the Mode 6 data might show that cylinder 3 had 45 misfires during the last cold start. This points to a developing issue, perhaps a small coolant leak into the combustion chamber or a carbon track spark plug. By looking at the test value versus the threshold value in Mode 6, you can see how close a component is to failing. If the threshold for a failing oxygen sensor is a value of 100, and the car is currently reporting a 98, the light is off, but the component is at 98% of its useful life. This is the peak of predictive diagnostics. Now, consider the 2026 pre-trip inspection for a long-distance journey. Imagine Chris is preparing for a 2,000-mile drive across the United States. He doesn't just check the oil level. He performs a systemic health check. He starts with the battery management system. Instead of a simple voltage test, he uses his tool to check the state of health percentage. If the BMS reports a state of health of 60%, Chris knows the battery's internal plates are sulfated, and the cold mountain passes of his trip could be the final stressor that kills the battery. Next, he performs a visual sweep of the chassis, looking for witness marks. A witness mark is a clean spot or a streak in an otherwise dusty area. If he sees a clean streak on a shock absorber, he knows it is leaking hydraulic fluid. If he sees a clean spot on a CV axle boot, he knows grease is being flung out by centrifugal force through a tiny tear. These are the physical echoes of mechanical failure. He then checks the tire date codes. In 2026, tires are often engineered with thinner sidewalls for better rolling efficiency. Historical data suggests that tires older than 6 years, regardless of tread depth, have a higher statistical probability of structural failure due to dry rot. We must also address the most significant shift in 2026: over-the-air or OTA updates in cloud diagnostics. Modern vehicles are constantly uploading telemetry data to the manufacturer. This creates a fascinating new diagnostic layer. Sometimes a car will behave strangely not because a part is broken, but because the software has a bug. Imagine if Chris's SUV starts having an erratic idle. Before he reaches for a wrench, he checks for TSBs, or technical service bulletins. In the digital age, the manufacturer might have already released a software patch that recalibrates the idle air logic. Conversely, he must be aware of cyber diagnostics. If a communication module in the car is hacked or suffers from a corrupted update, it can mimic mechanical failures by sending false data across the CAN bus. Understanding the difference between a mechanical thump and a digital glitch is the ultimate skill of the 2026 technician. As we conclude this 10-part deep dive, we return to the core philosophy. The car is a logical system of systems. It is a conversation between chemistry, physics, and code. You have learned to interpret the smell of coolant as a thermal warning, the rhythm of a misfire as a combustion failure, the voltage drop as an electrical bottleneck, and the fuel trim as a computer's cry for help. You are no longer a victim of the check engine light. You are its interpreter. The financial and safety implications of this knowledge are profound. Case studies from the mid-2020s show that informed owners spend nearly 40% less on repairs over the life of their vehicles. They don't buy parts they don't need, and they catch small leaks before they become engine-killing floods. They understand that a vehicle is not a static object, but a living, breathing machine that is constantly providing feedback. But as we stand at the peak of internal combustion diagnostics, the horizon is shifting. The United States is seeing a massive transition toward high-voltage electrification. The rules of diagnostics are being rewritten as we speak. We are moving from vacuum gauges and fuel pressure testers to megometers and thermal imaging cameras. The engine is being replaced by the stator, and the fuel tank is now a lithium-ion array. You have mastered the foundation of the automotive world that has powered our lives for over a century. You can now walk into any repair shop, any used car lot, or any garage in the country with the confidence of a professional. You know what your car is telling you, but are you ready for the next revolution? Are you ready to dive into the high-voltage world where a single mistake can be fatal, and the exhaust no longer exists? Because the Diagnostic Masterclass doesn't end here. It is merely moving into a new dimension. In our next series, we will crack open the battery packs of the future and show you how to diagnose the silent, high-voltage machines that are about to take over the American road. The age of the electron has arrived, and the masterclass is just getting started.